fluid flow that's coming into the motor to slow it back down again. Similarly, if the motor should start to, or at least the shaft start to stall or move at a slower speed, that influences the flywheels so that they move closer inboard to each other. So there's less centrifugal force. You'll pour more hydraulic fluid into the motor in order to speed it back up again. The valving in it is primarily controlled by a pilot valve. And again, we've got the introduction of hydraulic fluid from the pressure source that comes into a starting valve that they label as C. It's a governor control valve. That immediately pushes over one of the slides on a different valve that they label as H. It's a starting valve. And what that does is it pushes this plate over, a wobble plate. That establishes the initial direction of rotation one way. So it can't reverse itself. It can only go in one direction of rotation. From that point on, the speed is really governed primarily by moving this particular pilot valve piston back and forth, the governor control valve, and the opposing force would be the flyweights and this big spring that they have on it. So it limits the amount of fluid that's being directed ultimately into the cylinder block and will control the speed of the hydraulic motor. Examples of something like that, anything where we have to have the same speed all the time regardless of either pressure or the load that's being imposed on the shaft. So we'll use a hydraulic motor. In this case, it's non-reversible, but it provides for a governed type of speed. So it's a governed type of hydraulic motor. There's an interesting device that they have on back of the flyweight assembly piston. It's a pre-act spring. The pre-act spring prevents premature hunting of this pilot valve that's being moved. So it provides kind of a counterbalanced force against that piston, or at least against the control valve, so that it doesn't move too quickly or seek a position, in excess of where it's being commanded to. But the adjustment of it, sometimes they've got an adjusting screw on the back of the hydraulic motor, and it influences the spring pressure on top of the flyweight assembly. So again, we can somewhat alter at least the set point for how fast that motor is going to be driven or how it responds to torque. So, but that's what they have. A different type of hydraulic motor. This is a modification of a vane pump. And it uses vanes in it, but rather than attempt to produce flow, what we'll do is we'll introduce flow into the pump from a pressure source and have a recovery point at the return. But we can make the entire core of it, or the core of the pump, move. And what you're doing is you're trapping fluid between the vanes and the wall of the motor in order to make it rotate. These things can also be not necessarily governed, but they can be driven in alternate directions of rotation by using a selector valve that pours alternately fluid into the opposite cavities to make them work. But it's a vane type, so the rotor can be turned in either direction simply by reversing the fluid flow path into and out of the motor. Let's talk a little bit about flight controls and for aircraft. Well, I've already told you that for many hydraulic systems, they sometimes use a balanced actuator. In this case, I guess they've got a balanced actuator for the most part. But for a lot of aircraft, they use what are called tandem actuators for flight controls. These receive inputs simultaneously from independent hydraulic systems into a control spool actuator, or a control portion of the actuator that's physically attached to the physical actuator itself. When we port hydraulic fluid into each of the cavities, the cavities become pressurized and will recover fluid from the alternate cavities. This is an attempt by the airframe manufacturer to provide redundancy in the hydraulic system. If we have failure of one hydraulic system, well, what we'll do is we'll still be able to use maybe the other hydraulic system to power the actuator in order to make it move back and forth. So this provides for a degree of safety. A lot of military aircraft and some civil aircraft use tandem actuators. And it goes to the same control. You might be powering an elevator or an aileron or maybe a rudder. but nevertheless, you're using simultaneously two independent sources of hydraulic pressure. Some military aircraft, they define those different pressure sources as System A and System B, or sometimes they'll use maybe utility and primary control, but you're using two independent systems in order to be able to do it. The selector is incorporated into the actuator. So the input in some older aircraft is going to be a mechanical connection that moves a control spool back and forth to, again, provide hydraulic flow into the actuator cavities. In modern aircraft, sometimes the controlling mechanism that makes that spool move is going to be electronic. In a lot of flight control systems, the input that makes this rod move back and forth to port hydraulic fluid is also electronic in nature. So again, we can set a desired course or a path for an aircraft by commanding the actuator to assume a certain position. But when we talk about tandem actuators, they've usually got two cavities inside of the single actuator. It saves space too, but most importantly, we've got two separate hydraulic systems that are simultaneously driving an actuator. This is the idea as well. Sometimes they'll have, another term might be used as redundant. So they've got two actuators essentially combined into one, but they're being fed from independent hydraulic sources. There's a picture of this on page 188 of your airframe book. So redundant and I guess tandem kind of means the same thing. Rack and pinion actuator. This is still a linear actuator, but what we can do with it, we can move a piston alternately with a rack that's attached to the piston and then a pinion that rotates back and forth. Some Cessna landing gear, 172RG, I think, uses a rack and pinion type of actuator. The travel is usually about 90 degrees in order to make the gear come up and go down. There's another variation of it too. You can have a pinion, and as it rotates, it forces the pinions out, but you can see that it's got kind of two pistons on the inside of it in order to make it move. Sometimes also, again, maybe I'm thinking windshield wipers. Some of the actuators operate that way. Here's a close-up view of what you might find in some Cessnas for gear retraction. The piston could slide back and forth, but the teeth that are around the rack gear cause the pinion to rotate through an arc of about 90 degrees on it. The pinion shafts that hang out are attached to the gear. In Cessna, anyway, they use one rack and pinion actuator for one gear and another for the other gear. So you've got two in it for the main gear itself. Another picture. Oh, snubbing. A good illustration of being able to slow down an actuator at the end of its travel. What they use inside of the actuator is a device that works as a sleeve to cover holes progressively as the piston kind of moves to the ultimate end of its stroke. So they've got an operator that's on the inside that's spring loaded. When that piston containing that spring moves in one position, what it does is it blocks off holes that bleed hydraulic fluid into the chamber above it. And what that does is it slows the actuator down toward the end of the channel, at the end of its travel. And in some cases, what you might also find is an orifice check valve that's used inside of it as well. So maybe moving it in one direction, they're moving that operator over in order to snub it or control flow. But you may also find to move it in the opposite direction, they may use an orifice check valve in order to control its motion at the end of its stroke. And if we want to cushion the actuator so it doesn't come to a crashing halt, this is how we would do it. So the actuator will ultimately reach the end of its travel, but it's going to do so in a kind of a graceful manner. It's going to, at the end of its travel, it's going to slow down greatly before it reaches the end of its stroke. There's a lot of different ways that we can do that too. This is an example of another type of cushioned actuator that they use on the E-2 aircraft for the landing gear. It works in a way that's very similar to a shock strut. If you were to dismember a shock strut, what you find on the inside of them is a metering pin. And as the piston is being slid forward, the metering pin finds its way into an orifice opening. and that restricts the flow at the end of the travel. This one is kind of unique in a way too, because it's got a port that expels atmospheric air as the piston is being pushed over. And it's got a spring on the other side of it that will allow the poppet, I guess in this case also the cushion at the other end. Kind of unique also with the actuator too is one of the ports, this would be the down port for extension of the gear. It contains an integral shuttle valve. The normal extension pathway is for fluid to enter into the shuttle, so it displaces the shuttle valve in one way and allows fluid to enter into the cavity. And if we do it for emergency extensions, they use a confined gas under pressure, maybe a blow-down bottle in order to for emergency extension. So when we release that air charge, what it does is it pushes the shuttle the over, and it occupies the cavity in order for extension. So remember what I told you about shuttle valves. It doesn't necessarily have to separate two hydraulic systems. It just separates a normal from an alternate source of pressure. The extent, it says pressure is routed through the extent port into the feed tube. Fluid flow is restricted by the metering rod. So it looks like it comes in here, so the rod is inside of the cavity, so it can't really fully get over there. The piston head eventually contacts the poppet, which slows the movement of the spring by putting the spring in compression. Unpressurized fluid is expelled from the retract port at the same time. So the fluid is coming out of here, I guess, when it's being pushed over. And the air is drawn out of the outer chamber behind the piston. Retract pressure is rounded through the retract port to the outer chamber against the piston head. Piston retracts rapidly as unpressurized fluid, and the inner chamber is forced through the feed tube and out through the extent port. Air is expelled from the outer chamber from behind the piston. Sometimes, too, what you'll find in many of these actuators, there will be internal sleeves inside of the actuator. And, you know, I've already told you about unbalanced actuators. You know, you've got a disparity in force. The reason that they have the sleeves inside of the actuator is to provide for a double-acting actuator that is somewhat balanced. They're controlling the ultimate amount of surface area that's exposed to the fluid, and in that way, they can control not only the speed of the actuator, but have the same amount of force on both sides of it. So again, if you see some sleeves in it, sometimes it's for that particular purpose. Yeah, internal cylinders or piston sleeves permit equalizing the fluid displacement. So the same amount of fluid is being pushed out. Lock actuators. There's a lot of different ways that we can play this game too. If we have to have an integral mechanical lock in an actuator, like a landing gear, what we do is we make one by having maybe a particular part of the actuator slide into a recess and be held there mechanically, sometimes under spring pressure. In this case, they're using a ball lock. And what they're doing is they're forcing the balls to come out of a recess in order to make the actuator move. And then when the actuator moves to the alternate position, the balls fall back into a recess in order to provide for locking it. So this one is the top picture, geared down and locked. Balls are held in the race detents by a ball lock plunger. So I guess they're pointing over here. Okay, they got a ball lock plunger and they're holding the balls in their position. Down lock switch actuated by piston group shaft. This device over here is really coupled to the indication system of the aircraft for gear down and lock. So when the gear is down and locked, that this roller is in a recessed area, that completes the electrical circuit for gear down and lock. When we want to unlock the gear, we have to apply pressure against the spring in that piston. It causes the balls to drop free out of the recess, and then hydraulic pressure can eventually move the piston. But you're using a mechanical lock that you have to physically unlock with hydraulic pressure to get it to move out of the recess. Down and lock is recessed, piston shaft assembly retracts, and the gear is unlocked. So this would be the ultimate position for gear up. Okay. This is kind of like what we have on the S2F landing gear. They've got a finger lock type of actuator where they use fingers that fall into a recessed opening, again under a spring lock. And remember what I told you also, for all landing gear systems per FAA regulation, Part 23, the locking device that we have to have for hydraulic landing gear, or at least if it's hydraulically powered, cannot be hydraulics itself. It has to be a mechanical lock in some way that has to be unlocked in order to allow the gear to retract. You can't use hydraulic pressure in order to keep the gear locked in the down position. And there's a reason for that. Obviously, if hydraulic pressure is lost, there's a potential for collapsing the gear. So we have to have a mechanical lock incorporated as part of the down lock. Another type of internal lock. This one uses a locking block with fingers that are attached to the piston. In the unlocked position, the initial force of hydraulic fluid forces the spring to collapse, and then these locking blocks fall out of position with the fingers that are attached to the actuator, and then the piston can move. But again, you're using really a spring with these mechanical blocks that are holding the piston in the locked position. And that it can be unlocked hydraulically. However, you have to have the mechanical locking device installed so that, again, loss of hydraulic pressure won't cause the gear to collapse. Another type of locking ball type of actuator, maybe a different view of it. This one looks like it's in the locked position. The ball is held inside of the recess, and then we apply hydraulic pressure. It pushes a piston over, compressing a spring. The ball drops out of the recess, and it allows the piston to move. Better view. Okay. Let's talk a little bit about servo actuators. Let's go talk a little bit about flight control systems for aircraft. Now, this is kind of a cobbled together picture, but this gives you the idea of what we're trying to do with powered flight controls in aircraft. What we want to do is we want to limit the travel of the actuator to a commanded position, just like steering your automobile. So if we turn the steering wheel in the car, we want to be able to position the wheels that are on the ground to a certain amount of displacement. We do the same thing with flight control systems. Now, it's crude in a way because, again, many of the actuators for flight controls are balanced actuators. But for simplicity, just to illustrate the idea of a servo actuator working, they're using what appears to be a unbalanced actuator. The selector valve is physically coupled to the rod that's connected to the actuator to make the flight control move. So what we have is some type of connection over here that goes into the cockpit. It's a mechanical control in this particular case. If you pull on the rod that's attached to the connection point, what you're doing is you're positioning the spool, or what they call a pilot valve spool, in one position. What that does is it allows hydraulic fluid under pressure to be applied to through the selector valve, and then ultimately end up into the cavity of the actuator that it's attached to. But you'll notice here that the rod is physically connected also to a kind of an elongated, to a rod that extends through an elongated slot. So, okay, we poured hydraulic fluid into the actuator. The rod begins to move, and eventually the piston rod also on the actuator continues to move. But this rod eventually contacts the end of the slot. What do you suppose that does to this pilot spool valve? Repositions it to off. So if you want to continue to move the actuator, you're going to have to provide another force on the pilot valve spool in order to, again, pour more fluid into the actuator. But again, as the piston rod begins to move, the action of motion of the rod of that actuator ultimately will recenter the selector valve back to the off position. So what I'm trying to tell you is you're controlling the motion of the actuator by itself. As the device is able to sense its own motion, and at some point it shuts off hydraulic fluid in order to stop it. So this is the idea of what we use inside of a servo actuator. Sometimes they'll refer to these as power control units, PCUs, in aircraft. The key thing that makes it kind of turn itself off is this device called a sloppy link. It's an elongated slot that exists in the rod of the actuator to make it work. And it says, I'm giving you just a description of what they've given out of the book. It says, Figure 2.9 shows a typical hydraulic servo. In operation, when the pilot valve is displaced from center, pressure is directed to one chamber of the power piston. The other chamber is open to return flow. As the power piston travels, the pilot valve housing travels because the two are attached. Okay. The pilot valve itself is being held stationary by the operator, and the ports again become blocked by the lands of the pilot valve, stopping the piston when it is moved the required distance. So again, it turns itself off once a particular amount of motion has been completed. If you want to make for more motion out of the actuator, you have to pull the pilot valve spool further in order to get the actuator to move. Then ultimately it stops moving. The sloppy link. Notice the sloppy link in 2-9. It is the connection point between the control linkage, pilot valve, and servo piston rod. Its purpose is to limit the servo piston to be moved either by fluid pressure or manually. The sloppy link provides a limited amount of slack between the connecting linkage and the pilot valve. Because the slack between the piston and the end of the connecting linkage, the pilot valve can be moved to the on position by connecting linkage without moving the piston rod. Could be electrically controlled as well, I would imagine, but again, what you're doing to keep the pilot valve progressively open and exposed to the servo or the servo actuator, what you have to do is you have to continue to pull on that pilot valve spool in order to keep it porting hydraulic fluid. Sometimes they have a bypass valve in these devices. The bypass valve is kind of interesting. It allows for interchange of hydraulic fluid. And in normal operation, when the system is working, the valve is blocked. You don't have any ability for fluid to go through the valve. However, let's say we've lost our hydraulic pressure. What we want to do is we still want to be able to move the piston back and forth. So we want the cavities to be operational. The valve opens in order to allow for the exchange of hydraulic fluid back and forth inside of the actuator. So it's what they call a bypass valve in order to allow for continued motion. Maybe we don't have hydraulic pressure available here, but we still have to be able to move the actuator back and forth, maybe manually. So it provides for the exchange of hydraulic fluid to enter one side or the other by mechanical motion. So what I'm trying to tell you is if the hydraulic system goes haywire, we still have the ability to manually move this piston back and forth, but it's going to be manual in nature. You're no longer going to have any hydraulic boost, but nevertheless, you can still manually control the aircraft. Something else, too, to kind of consider. We've talked about this concept of boost. You all remember when we first started talking in the class about force, area, and pressure. In this case, the pilot valve spool is extremely small. So you're porting hydraulic pressure into this thing, maybe, say, 3,000 or 5,000 psi. But if you look at the actuator that it's actually moving, it's much larger. This kind of explains how we're getting powered movement, or at least multiplication of force for hydraulic systems. So this thing is actually minuscule in size for the amount of surface area that's exposed to fluid. And again, you may have 5,000 psi in here, but again, very small amount of force is actually developed at this point in order to move it because of the surface area. However, what's connected to the flight control, the piston is relatively large. So this is what's giving you the opportunity to be able to build hydraulic force, multiplier of force. Maybe a better view of what's happening with this type of actuator. And again, the pilot valve and the selector valve is connected directly to the piston rod. So as the piston rod begins to move, the selector valve is progressively shut off from hydraulic pressure once it reaches a certain amount of travel. And it's all done because, again, of that sloppy link. This provides for kind of a loose fit connection between what's controlling it and the actual motion of the actuator. And the bypass valve, again, this one's open. This would assume that maybe we've lost hydraulic pressure. We are now manually controlling the flight control. So we've got a mechanical connection, but this allows for the exchange of hydraulic fluid to the opposite side of the cavity, back and forth as required. Another picture. I stole some pictures out of an old Navy flight Navigator manual or a training manual, and it shows you what they used in some early aircraft just for simple flight controls. This one is for an aileron from a Navy A4. It uses a portion of the circuit is mechanical. They'll use cable actuation through a mechanical connection that directly connects to the aileron. In the event of hydraulic failure, the disconnect that the pilot has is available here. This is a disconnect, so it's completely mechanical for operation of the flight controls in the event that the hydraulic system fails completely. Normal operation, they have a utility hydraulic system that provides an independent source of hydraulic pressure, making it available to one cavity. The other side is a dedicated flight control system hydraulic circuit that provides hydraulic fluid to the alternate, to the other cavity in the tandem actuator. Both of them work in unison, usually through a tie rod. And when we move the stick in either direction for left or right, what we're doing is we're simultaneously opening pathways through these pilot servo valves into the cavity. And then the actuators will move in response in order to make the ailerons displace. So pretty simple. Notice also something too, they've got a device that they call a load field bungee. The load field bungee in early aircraft is really nothing more than a compression spring. There's no sensation of how much force you're actually applying when the ailerons are being moved. So this provides for a degree of artificial feel. So in order to be able for the pilot to sense that the ailerons are actually being displaced, they provided a spring that can be compressed in order to be able to provide for that sensation. This is crude. Modern aircraft usually use something different. They've got an attachment, or at least a device that they call a Q unit in a lot of hydraulic systems that replaces that load bungee. This works really well for aircraft that fly at moderately high speed, but not very fast, that have a great degree of surface deflection. But it doesn't work well for aircraft that have a very small degree of travel for the actuators and fly at very high speed. So it's not really an effective way for controlling load, or at least sensing load that they're having. Another one, this is a Navy A4 also. And in this case, they've got a tandem actuator, and again, they've got the the control valve for the PCU incorporated into one unit. Normal operation, you're porting, again, hydraulic fluid from independent sources, in this case, hydraulic flight control system and utility, into pilot valve spools. And then simultaneously, you're powering the actuator in one position or another, depending upon what you're trying to do with the elevator. And mechanical override for it, they usually have some type of disconnect, and again, it reverts to a mechanical operation simply by unhooking this. So the pilot has the option of disconnecting it, and from that point, it provides for direct control by push-pull through manual operation. I don't know what they have in here for bungee. Maybe they don't. I don't know. So nothing for load field, I don't think. And this one is for a rudder control. This is a Navy A5. They've got a load field bungee in the circuit, and again, a spring cartridge. Seems like anything that has got a spring or a spring-like action they refer to as a bungee. Even if it were to have a pneumatic charge in it that would be compressed, but they call it a bungee. So anyway, they call it a bungee. Rudder pedals, deflection of the rudder either way, goes through cable and through pulley, but ultimately it terminates into the control for the rudder, the pilot valve spool. Similarly also, you'll notice that they've got a tandem actuator, and coupled with it, they have two pilot valves. The pilot valve moves left or right. What it does is it pours simultaneously fluid into the actuator in order to displace the actuator. And then when it moves in the other direction, the spool slides over. And ultimately the fluid is shut off, again, because of a sloppy link that they have in the component. So it controls it, or it shuts itself off after a certain amount of deflection. You'll notice something here too. They've got something kind of weird. I don't know what you can infer that to be. It says to AFCS, what does that mean?
Flight control system.
That's a flight control system. In a lot of the flight control circuits that are automatic, what they do is they've got a reed type of device, and what they'll do is they'll bias the motion of this pilot valve spool by using two diverter types of squirter valves that work on the reed. And what it will do is by introducing electric current into the coils that are next to that reed, we can restrict or allow hydraulic fluid to flow, and that influences the motion of that pilot valve spool. I'm going to show you tonight after dinner break, I'll show you what they use for an anti-skid system. And it works in a similar way. They use a device that's really part of a servo, they call it a torque motor. And what it does is it limits hydraulic flow in order to control the motion of this pilot valve spool. And they use it in anti-skid systems quite frequently for some corporate aircraft. If they want to prevent a skid from occurring on tires and wheels, they dump hydraulic fluid going to a brake. So it prevents the rapid spin down of a wheel and tire, and so that it reduces the potential for a skid occurring. It'll allow the tire to somewhat slip, but it won't develop a skid. It just reduces the speed slightly, but it dumps the hydraulic fluid. But I'll show you how that kind of works after dinner break. And well, here's a good example of it. We don't know what type of actuator this really powers, but you'll notice down at the bottom over here what they have is a servo valve type of device, and they call this, in a lot of installations, they refer to this as a torque motor. Our flight control system will provide electrical signals to these magnets, or the coils that surround the permanent magnets. And what it does is it will bias this reed one way or the other. In a normal operation, hydraulic fluid is going through one of these nozzles, actually both of them at the same time. But if we're able to move this reed over, we'll restrict hydraulic pressure in the line. And we can allow that to have happen, we can allow that to control the motion of a pilot valve spool. We create pressure in a cavity. And similarly, if we restrict the flow in this line, what we can do is we can force the pilot valve spool to be pushed in this direction. That ultimately commands the direction of motion for the actuator that's attached to it. So our flight control system really is producing an electric signal or electronic signal that's moving this reed one way or the other. Okay. Let me just kind of show you this real quick. This is I don't know if it's a handout. This will describe it. It's in your student PowerPoint as well. More of an engineering type of thing in order to actually make it work, but sometimes they just got a coil that moves the reed one way or the other. But ultimately, it influences the pilot valve so that it can control the direction of the actuator that's moving what we want to move. So, let's see what else I've got here. No audio. The idea is to control the motion of this device, which then causes the pilot valve spool to be moved in order to make the actuator piston move as well. So you can see what they've done is they've got even a better picture. Here's the pilot valve spool. They're showing you the red as being pressure. But anyway, torque motor type of control for a lot of the electronic flight control systems. So, but I'll show you something after break to kind of sum it up how it works. They're really complex. I mean, this picture is from a MiG aircraft, but it kind of describes what's happening. I don't know that this link works anymore. It was a part of flight control, but maybe deactivated. Let's see. Yes, it's been taken away. I had a YouTube video that showed the motion of a hydraulic actuator with a ground support source, but you could see that they use springs for load feel in it, and they also used balanced actuators to make it work. Man, talk about complex. This is Bell's Augusta tilt rotor actuator, servo actuator that they have. And again, don't ask me what port is what, I have no clue. Okay. And again, another rudder power control unit. This one has got a balanced actuator in it, and I don't know what they use for, well, they probably have got a method of disconnecting it should the system not work. But the method of controlling the pilot valve spool, they use a servo valve, again, that can position this pilot valve, which ultimately controls the motion of the actuator. And usually a sloppy link, in order to limit the amount of travel, they've got what they call a follow-up lever in order to do that. But if you attend a particular service school for a certain aircraft, they go into excruciating detail on how these things kind of work. But it varies from aircraft to aircraft as far as the architecture is concerned. Another one, boy, you know, they just, one of the textbooks gives you this picture, but they don't show you exactly what's happening in it. Anytime they talk about a follow-up linkage, this is a kind of equivalent to the sloppy link that provides for turning off the actuator once a certain position has been commanded. So that's the idea of follow-up. An example of a Jet Ranger, the actuators are attached to the, or at least are move the swash plate of the helicopter in order to change directional motion, and it tilts the upper swash plate in order to provide for motion in pretty much all axes. You've got three actuators that are used on that aircraft. One of them is a collective actuator, and what that does is it changes the pitch of all of the blades at the same time by pushing up on the swash plate all at once. The other actuators really tilt the swash plate in order to provide for lateral and fore and aft motion of the aircraft. But what it's doing is it's disrupting the plane of rotation of the rotor blades to provide for motion. These are power control operated actuators as well. This part of the housing is really where the pilot valve spool is really contained. The motion from push-pull rods influences the pilot valve spool, which then diverts hydraulic pressure and provides a cavity for return, or a return path back to the reservoir. What do they do in this aircraft for malfunction? Well, they've got a solenoid valve that's in the aircraft. If the pilot wishes to not have boost of hydraulic pressure, the solenoid valve is turned off, and what that does is it provides for direct mechanical connection from the push-pull controls into the servo valves. But again, just like in this case, there's a bypass valve that's incorporated into each of the units, and what that does is it provides for exchange of hydraulic fluid to either side of the actuator when you're using mechanical control. Quick disconnect fittings, again, maybe for ground power use if you want to operate it. This is going to be a power pack. We've got a reservoir, a pump, and a regulator contained in one device. But again, an idea of what they use for like a Jet Ranger. And I don't know if you want to talk about this. Older aircraft is really complex. They sometimes use rack and pinion type actuators in order for nose wheel steering. And a lot of cable runs were used in it with pulleys in order to make the pilot valve run. You can read about this if you wish to in the Merrill Fluid Power book. Some cases, they had kind of a weird type of valve that they used in it in order to control the motion of the nose gear. But, there's the selector valve for it, and this actually goes to the actuator. Steering damper. This is what they use in modern aircraft for artificial feel. Remember I told you in some of really early aircraft, they use a spring that's compressed in order to provide for artificial feel. That works really well when there's a lot of control surface deflection and the aircraft is relatively low speed. However, for tactical aircraft or aircraft that fly at high speed, where you have a limited amount of surface travel or surface control surface deflection, it's not practical to use springs for that type of deal. You have to use something that provides for a force field to simulate load. So they use a device that's called a Q unit, and it receives signal in most aircraft from an air data source, usually from an electronic monitoring system, just like repeato-static. The faster that the aircraft goes, what it does is it provides for a greater force field in order to counter the motion of the actuators. So, but in this case, they use a separate actuator. They call it a load field jack that's connected to the flight control that provides for a limited amount of resistance in order to make the simulate for load. And but again, it's called a Q unit. As the aircraft speed increases, it increases also the amount of resistance required to power the flight control. And again, military and commercial aircraft, high speed, low control surface deflection, sometimes used. And springs are usually used when they have aircraft with lower speed. You know, those early military turbine engine aircraft that I showed you, those are low speed considered today anyway. And kind of crude to see springs, but they did it in an old aircraft. Higher, a lot greater control surface deflection, and springs will work in that particular case. I'm going to have you watch a video if I can find it. And maybe we'll show this at, oh, that's taken away. Maybe I can find it for you during dinner break. I don't know if you're aware of it, but the Boeing 737 had growing pains. And there was a particular problem in some versions of the Boeing 737 with a problem they call rudder reversal or rudder hardover. And I'm going to show you a little bit of a video on it. I'll also send you a link that you can read. But at least a couple of aircraft crashed as a result of having an uncontrolled rudder or a rudder that was deflected for full deflection and ultimately burnt a hole in the ground. And kind of tragic in a way. The cases were investigated by the NTSB, and a lot of conclusions were drawn from it. One big thing that was noticed in the design of the 737 aircraft, they use a dual spool type of controlling mechanism for the actuator. Even though they're separating two distinct different hydraulic systems, the spool itself, it's like a slide covers another slide. So it's not like having two separate pilot valves. They've got two sleeves that slide over each other in order to port hydraulic fluid. This is very much different than other Boeing designs. The 707, 727, 747 have different pilot valve spools that independently control the flow of hydraulic fluid. What they guessed from the NTSB investigation, a couple of things. The spools or the slides became stuck, and they could never really explain why. They thought maybe in one case, if the servo actuator had been taken apart and the spring on the inside of it had been reversed in position or been put in backwards or omitted, it might cause the condition to occur. Another thing that they thought as well was the potential for thermal expansion to have an effect in the locking the slides together. Well, so they heated hydraulic fluid and they subjected the servo actuators to cold temperatures. They were never able to conclusively prove that that was the case either. Another thing that they kind of concerned themselves with was contamination of hydraulic fluid. So they thought maybe one of the sleeves was being blocked by debris. Well, So what did the NTSB eventually do? They provided for Boeing to redesign and retrofit existing aircraft with a hydraulic circuit that replicates previous designs. So that's how they did away with it. I had a friend that worked for Southwest, actually still does, he works for Southwest Airlines. And they were doing a test of one of their rudders on the 737 aircraft in Phoenix. And he remembers standing up near the rudder, and they were checking the operation of the rudder, and all of a sudden the rudder, the trailing edge of it became a blur. You know, it just was completely uncontrollable. And obviously, if they hadn't done the aircraft, the potential was there for that aircraft to have that problem. Early in the discovery of this problem, pilots were taught to immediately pull the circuit, the electrical circuit breaker for the flight control system in order to just have manual control of the circuit. And because no amount of foot pedal pressure could relieve it once it began. So they didn't know exactly what to do. But again, the NTSB was never really able to come up with a definitive answer of why it occurred. They just followed a path of retrofitting the aircraft to the previous design in order to eliminate the problem. But very tragic how it works. It's now what, 5:41? Why don't I see you back here at 6:30?